So today we are going to start with haloalkanes or halogen alkanes or alkyl halides, three different ways to identify the same thing. This is basically when we had alkanes and we did substitution in them and we created haloalkanes. Like we used, remember in O levels, we had methyl and we would react it with chlorine and this will create chloromethane. Now we know that it was free radical substitution that the process was, and basically this hydrogen was displaced by the chlorine and that hydrogen went over there. So there was the initiation, propagation, substitution. But उससे जो भी हमारे पास बना, that is haloalkane or halogen alkane or alkyl halide. So when you displace 1, 2, 3, 4, whatever number of hydrogen atoms with some halogen, this creates haloalkanes. And the method is free radical substitution for that. So for example, if I gave you this compound, what's its name? It is chloropropane because the main long chain is this one, and there's 3 carbons in them and in it, and there's chlorine on the second one. So this is 2-chloropropane. This is a haloalkane. Similarly, you could have this thing, and is this a chiral center here, this atom? It is because it's attached to chlorine, hydrogen, and this bromine thing and that carbon on this side. So this is a chiral center. And this one is, what is it? 2-bromo, 3-chloro, 1, 2, 3, 4, 5, pentane. Now, how do you name bromo and chloro? In the alphabetical order, okay? So bromine, it starts with B, so it comes first, and chlorine starts with C, so it comes later, and iodine starts after that, and fluorine somewhere in the middle. Okay, so you always name them in alphabetical order, but you will not lose marks if you don't do that. So you can obviously create isomers of this. For example, this one right now is a chiral center with the chlorine at the top and maybe this thing on the side and a hydrogen in the dotted line, and the wedge thing can be joined with what is that thing? CH2, CHBr, CHBr, and CH2. Yeah, so it's a chiral center, and this you can obviously reflect. And when you reflect it, you get the wedge here, the dotted line here, and the solid line here. So that makes it CHBr joined with CH2. So all of that is there. So you can get these isomers. You can also get other isomers. For example, if I had bromobutane, for example. So this is butane. I could add bromine here, or if this is butane, I could add bromine here, and I'm getting 2-bromobutane or 1-bromobutane, and then 2-bromobutane also is chiral because of this carbon in there. So that also has the mirror image as another isomer. So you have to pay attention to different isomers and how we make them. And of course, all of that comes from where the position of the substituted carbon is. So for example, if I told you that C4H9Br is a compound bromobutane, how many isomers can you come up with? So let's start. This one is really simple, 1-bromobutane. The other could be 2-bromobutane, but 2-bromobutane I've already drawn it. And the thing with 2-bromobutane is that this is chiral, as you can see. Now, how do you draw this? One way of making chiral is you put this carbon for the chiral in the center, obviously this one here, and then I have CH3 on one side. So CH3 on one side, hydrogen on the other side, and then I have this the ethyl branch, so C2H5. Now, the isomer for this would be the reflected version of it. So CH3, hydrogen, C2H5, and Br. So that's now 3 isomers in total. Then I can have branches for this. For example, I can have, so let's take it like this. I take the first 1-bromobutane, but instead of drawing the last leg, I just take that and I place that, sorry, this part over here. I place it maybe here. Because the moment I do that, I've created a branch. And now this one is a methyl attached to second carbon. So now this one is 1 bromobutane. These two are 2 bromobutane, and obviously they are the optical isomers for that. And this one is 1 bromo 2 methyl propane. Now I can
So
even
how
do
is it
one.
2 methyl? Wouldn't it be 3?
No, the first carbon is this, second carbon is this, third carbon is this. I could also move this bromine, so I could take the 2 methyl propane and I could add the bromine here. I could do that, move this from here all the way to here. And if I do that, I will end up with again, this is 2 bromo, 2 methyl propane. So these are the 5 isomers of C4H9Br. So you can clearly see that depending on what you're substituting in and where you're substituting the location, and if you're getting optical isomers, there are many different isomers that you can draw for just one substitution of halogen. Another thing that you need to know about this, so two rules that you need to know. First of all, every chiral center doubles the isomers that you can get, because every chiral center causes it to have 2 isomers. So there's the 2 in there. So if you have 2 chiral centers, you are likely to get 4 different isomers. 3 chiral centers, you're likely to get 8 different isomers, because 2 times 2 times. And then that's one way. Then we also classify halogen alkanes as primary, secondary, or tertiary. The idea is again really simple, that you look at the carbon that's attached to halogen. Halogens we usually represent as X. And then if that carbon is attached to one carbon or one alkyl, this is primary. If it's attached to 2, it's secondary. If it's attached to 3, it's tertiary. Of course, it's not that it's always attached to just one. It is also attached to hydrogen when that's the case. So depending on how many carbons it's attached to, it can be primary, it can be tertiary, it can be secondary. And that has a role to play in its properties. But let's talk about the general properties of halogen alkanes. First of all, their physical properties are that they're all colorless. We know that halogens are not colorless. Halogens have distinct colors. Fluorine is yellow, chlorine is yellow green, bromine is red brown, iodine is black solid. There's a clear distinction in the color there. But when they react, they go colorless. Okay, the halogen alkanes that we have, organic compounds, they are colorless. Interestingly, even though they have this slightly negative and slightly positive charge, in general, they are immiscible in water. They're insoluble in water. And the reason for that is that, first of all, their density is much heavier than the density of water. Secondly, the longer the alkyl chain, the more dominant London dispersion forces become. Because the alkyl is going to decide the length of the molecule. Chlorine, bromine, iodine are just one small atom in there. The rest of it is the alkyl and the hydrogen and everything. They decide the London dispersion forces, and that is why mainly it's the London dispersion forces that are dominant force in these compounds. So they're not very soluble in water. They have a very pleasant smell, most of them, and their boiling points are higher than their alkanes. So, for example, if I take butane, bromobutane will have higher melting point. And again, the reason is because even though the main induced dipole is the main force there, uh, the strength is increased because of this polar part. So it is slightly more, the boiling point is slightly more, the melting point is slightly more, but not as much. So here's a graph to represent that. So if you look at this graph, then what's happening is that if I have the first alkane, it has a boiling point that's really low. It's a less than minus 150. But the first haloalkane has this as its melting or boiling point. So you can clearly see that the chloromethane has a boiling point that is greater than minus 50, but the simple methane has a boiling point that's less than minus 150. So that's a big difference. Similarly, chlorobutane, sorry, 1-chloroethane has boiling point that is greater than zero, but simple ethane is also a gas at room temperature. So these things, their boiling points are more than the boiling points of their uh, other uh, alkanes. But here's a very interesting phenomenon. If I take the different bromine, chlorine, and all that, then this is the criteria. The chloroalkanes have weaker or lower boiling point than bromoalkanes, and bromoalkanes have lower boiling point than chloroalkanes, and that is something that we usually uh, don't expect, because students always think that, oh, chlorine is more reactive than bromine and bromine is more reactive than iodine, so everything should be more for chlorine and less for iodine. But this is clearly the opposite trend, and there's a very simple explanation for this. The reason this happens is because boiling point depends on forces. So the forces in iodoalkane are stronger than the forces in chloroalkane. Can you think of a reason why that would? It's the same reason why chlorine is gas but iodine is solid. What do you think? Why would that be the case?
So maybe because more electrons, so the electron cloud is bigger, so stronger.
Exactly, that is the case. Very good, Shabash. So the electron cloud is bigger. There is more electrons in the iodoalkane compared to its counterpart in chloroalkanes. So obviously, the London dispersion forces that are caused, or even permanent dipole forces that are caused, are much stronger than the other ones. That is why iodoalkanes, for the same number of carbons, are going to have higher boiling point than chloroalkanes or bromoalkanes. And yeah, that's the case. Similarly, the other trend for solubility, we've already talked about it, that even though halogen alkanes have one polar bond, that is just one bond in the whole molecule and it's not that dominant. So the primary force that is there is the London dispersion force, depending on the chain, the how long the alkyl chain is. And if not London dispersion, a permanent dipole. So it's not the hydrogen bond, which is why it doesn't really dissolve in water. Smaller molecules may slightly dissolve, but sparingly dissolve, but larger ones will definitely not dissolve in water. So we can just regard them as insoluble in water and soluble in organic solvents like petrol or propanone and all that. So that's the physical properties. And there's two questions about physical properties that are asked. Number one, why do they not dissolve in water? And number two, why is their boiling point higher than that of alkane, and why is there a trend in the boiling point of different halogens with the alkanes? So those are the two questions that are usually asked, and we have answered those. Now let's talk about their reactivity. Here's the thing. Again, in O level, in AS chemistry, organic chemistry, always stick to the very basics. The more clear you are to the basic ideas, the better your chemistry will be. So the fundamental relation of charges is that positive attracts negative. That's a very fundamental thing. This is the thing that we saw in alkenes. In alkenes, the double bond had this pi cloud of pi electrons in there. There was a cloud of electrons, which was negative. So they attracted electrophiles. So any electrophile coming in, it was being attracted by these. And sorry, it's the other way around. The electrons attacked it. Similarly, even if there was a slightly positive charge, it will still attack them. And that's why we got electrophilic addition. In haloalkanes, it's the opposite way. In haloalkanes, so for example, in this case, I have slightly negative charge here and slightly positive charge here, and the alkane is the more reactive thing. So what's going to happen is that that alkane is going to attack a nucleophile. Okay. So basically, this positive charge in here, any nucleophile that is coming out on the side with a lone pair with a negative charge, if it looks at that positive charge, it will just not be able to resist. It will go on and attack the positively charged thing. Okay. And when that happens, it pushes the electron towards the alkene, that the halogen that. So listen to it again. In alkenes, we did not have polarization. We did not have slightly positive charges, but what we did have was slightly delocalized electrons of the pi cloud, and they were negative. So any slight positive charge passing by, they would immediately attack it. In this case, any negative charge, the moment it sees a positive charge, it's going to attack it again. It's the same thing. A negative charge looks at positive, attacks it. In alkenes, the negative was inside the alkene. In halogen alkanes, it's the positive that's inside the alkene. It's the negative thing that's going to come and attack this halogen alkane. So any nucleophile with a negative charge will attack the positive charge inside the halogen alkane. If you're clear on that, that negative attacks positive every single time. Now, you might be like, why are we not saying that positive attacks negative? Because all chemical reactions are done through electrons, and we just focus at what the electron is doing. So our perspective is always from the electron's point of view. That is why I'm focused on the nucleophile. I'm focused on the electrons, the negative thing, what it is doing. So with haloalkanes, the negative thing is going to come and attack the slightly positive charge, the positive pole in there. Now, there are two ways of doing that. First of all, nucleophile cannot attack it from the side where X is. Why? Because if this nucleophile were to approach it from this side, it will be repelled. It will be repelled. Why? Because the negative charge in here, this negative charge, will repel this negative charge. So nucleophile has to be sneaky about it. It has to come from the side where there is no negative charge. It has to approach the positive charge. Now, whether it succeeds in that or not depends on how approachable the positive charge. The idea is pretty simple. You have a carbon inside this R thing. There's a carbon in there that's attached to an X. It's attached to obviously other things. There's the other things in there and it's attached to them. And the nucleophile that's coming in with this electron, with this thing, there's a slight positive charge, slight negative charge. The moment it sees it, it attacks it. But whether it's able to attack it or not depends on how crowded this carbon is. If this carbon is joined with small atoms like hydrogens or one methyl, like there's one methyl here and the other is just hydrogen. If it is a primary carbon, then it's really easy to approach. Okay, so nucleophile just comes, attacks it from the opposite side of negative. When it pulls in there, when it comes close, these electrons are pushed towards halogen, and so the reaction begins. But if this carbon is very crowded, if instead of having something like this carbon has what many other atoms around it. If instead of having just this hydrogens, it's having like C2H5 and C3H7 and C5H11 or something like that. It's a big molecule and the carbon is deeply buried in other alkyl groups around it. It's not going to be easy to approach it. It's very crowded in there. So this nucleophile will not be able to approach it. So what will it do? It will do something, or it will wait for this to leave. It will have to obviously wait because that carbon is not approachable otherwise. So it will wait for that to leave. And when it does that, obviously, this will come and take its place. So two ideas. One, if the carbon is approachable. What are approachable carbons? Primary carbons. If they're approachable, then it attacks while X is there. But if it is not approachable, if it is crowded, and what is it when it's crowded? When it is tertiary carbon, it's crowded. There's so many other carbons around it. It's not able to approach. It waits for X leave. So first X has to leave, then nucleophile attacks. Now this thing is going to happen in two steps. And this thing is going to happen in one step. So the attack is going to be at the same time when X is leaving, if you have primary carbon. But if you have tertiary carbon, it has to first leave a space out there, and then nucleophile will attack. Are you understanding this? There are two possibilities here. So which one happens depends on how crowded the carbon is. And the reason why this happens is Now, it will also affect the rate of reaction. In the left one, when it happens in two steps, the rate only and only depends on concentration of one compound. Okay, the rate just depends on concentration of halogen alkane. But if it is going to happen like if it is going to attack at the same time, then the rate depends on concentration of both X and the nucleophile that's coming in. So again, here rate depends on just haloalkane, its concentration. But here rate depends on concentration of both haloalkane and the concentration of the nucleophile. And because of this, we call the left one SN1 and the right one SN2. Okay. So what does that mean? What's happening here is that a nucleophile is coming in and pushing the halogen alkane out, the halogen out, which means this is substituting the halogen. Halogen goes away as a negatively charged thing as a nucleophile, and the nucleophile comes in and displaces it. What do we call reactions in which there is displacement in organic chemistry? What do we call them? Over here in the very first reaction, hydrogen was displaced by chlorine. What did we call this reaction? Free radical substitution. The kind of reaction substitution and free radical is the particle involved. Over here, it's the nucleophile that's the particle involved, and this is substitution. So we call it nucleophilic substitution. SN is nucleophilic substitution, and or you can also call it substitution of nucleophile. And 1 and 2 tell me what does the rate depend on? Does it depend on just the concentration of haloalkane, or does it also depend on the nucleophile? So these are the two ways in which this happens. Now, of course, in your exam, you can't write that this carbon is crowded and this carbon is not crowded. So the reason we say that is again because of inductive effect of alkyl groups. Because here's the thing. When this over here, when this X leaves, this carbon gets a positive charge on it. It becomes a carbocation, right? If you took away the halogen, and this is very important, so pay attention. If you took away the halogen from this haloalkane, this carbon will become a positively charged carbon, a carbocation. And a tertiary carbocation will have inductive effect coming from 3 carbons stabilizing it. So tertiary carbocation can stay as a positively charged particle. But this carbocation will never be able to sustain itself because the only thing providing it inductive effect is this methyl group, if it even has that. So primary carbons, if they try to make carbocations, that will be very unstable. But tertiary carbons are better at making carbocations, which means that now the moment it gets a carbocation, a positive charge on this nucleophile gets some time to attack it. But if this is not able to sustain itself as carbocation, वो न्यूक्लियोफाइल को मौका ही नहीं देगा आने का, उसको जाने ही नहीं देगा, वो कहेगा नहीं भाई मुझे डर लगता है तुम नहीं जाओ. But this is able to withstand ये जो जुदाई है उसको वो बर्दाश्त कर सकता है. And that is why the tertiary carbon is able to withstand being a carbocation. It is able to borrow some time before the other thing can come and replace the halogen that left. But this halogen, if it leaves, ये नहीं रह पाएगा उसके बगैर. And that will be very unstable. This is why the primary carbons do not prefer making a carbocation. They're like, अगर ये जा रहा है तो फौरन इसकी जगह दूसरी replacement आनी चाहिए भाई. But अगर ये जा रहा है तो ये बर्दाश्त कर लेगा. So if a school had 2 teachers of chemistry and one of them left, the school can still sustain itself using the other chemistry teacher. But if there's only one chemistry teacher, the school is in a very unstable situation. If that teacher leaves, masla ho jayega. So you need a replacement right away. It's kind of like that. सो इसकी बार्गेनिंग पावर, सस्टेनेबिलिटी इसकी कम है, इसकी ज्यादा है, because of the inductive effect of these carbocations. Okay, so that is why this prefers SN1. वो वेट करता है, वो कहता है ठीक है ये चला जाए फिर अगला आए, कोई मसला नहीं, ये वेट नहीं कर सकता प्राइमरी कार्बन. So it has to replace the leaving halogen with the new nucleophile that comes in. ये clear है सबको?
Sir, if the primary one isn't able to get a replacement, what happens then?
It doesn't let that leave. अब उसमें ये होता है कि sometimes situation is कि वो फिर भी हो जाता है. But think of it like this: if I have two molecules, let's suppose I have CH3, CH2Br, and I have CH3 in a branch with CHBr, and I have CH3 in another branch with CBr, then the chances that this will undergo, like it will leave and wait for the new nucleophile to come, if that is the chance 1, मतलब अगर वो एक दफा या the rate of this reaction is 1, let's suppose कि ब्रोमीन को वो जाने देता है, वेट करता है, और अब उसकी जगह नया न्यूक्लियोफाइल आएगा. अगर वो वेट करने का रेट उसका 1 है ना, तो इस रिएक्शन के उसी काम को करने का कि इस ब्रोमीन को जाने दो, वेट करो, कार्बोकैटायन सस्टेन करो, एंड देन द न्यू वन कम्स इन. इसका रेट इज अराउंड 30, सो द रेट इज मच फास्टर. वो कहता है हाँ ठीक है करो करो फॉरन, कोई मसला नहीं. बट द रेट ऑफ दिस वन, द थर्ड वन डूइंग इट इज, टेक अ गेस, कितना होना चाहिए? 3 जगहों से इंडक्टिव इफेक्ट आ रहा है.
Sir, can you explain this again? Like, what is this the rate of?
So Samin's, Meher's question is that if it is not able to wait for the new nucleophile to come in, but we still force this bromine to go out. If this bromine goes away and now the carbocation has to be made, then how likely is it to sustain that? Well, what does it do in that situation when there is no nucleophile? तो मैं ये बताना चाह रहा हूँ कि the chances of that happening कि ये bromine चला जाए और carbocation बन जाए and then the new nucleophile comes in, if the chance of that happening on this primary halogen alkane is 1, if when this happens the rate is 1, then that same thing happening on this secondary carbon will be around 30. It's 30 times more likely to do it, or the rate of reaction is 30 times the rate of reaction of this thing. कि कार्बोकैटन बनेगा और फिर वो वेट करेगा और फिर उसकी जगह नया आएगा. Of course वो वेट बहुत थोड़ा सा होता है, in nanoseconds. Even nanosecond is too much, femtoseconds. The chances of this in happening and this sustaining and taking this route for this tertiary carbon is 60 million. So tertiary carbon is able to hold its ground as a carbocation, but primary carbon is not, which is why primary carbon will never opt for this route. हाँ आप कह सकते हो कि नहीं कोई तो करेगा, हाँ करेगा, maybe 1 in a billion molecules might do it. Another way of saying the same thing is that the activation energy for primary carbocation to be made is much higher than the activation energy of tertiary carbocation to be made. So it will not undergo this route, it will take this route. The moment this nucleophile leaves, the other nucleophile comes in. वो parallel में उनको displace करेगा. It will do it in one step. एक जाया और एक दूसरी जगह फौरन आ गया. But tertiary carbocation is more likely to first let this one leave and then allow the next one to come in. वो replacement का procedure थोड़ा slow कर सकता है because it has inductive effect on its side supporting its process. So exam में वो आपसे पूछता है कि why does this particular compound favor SN2 more? SN2 का मतलब है कि जिसमें वो one step में हो रहा है. So this favors SN2. So if I were to write the favorable things, this will favor SN2, this will favor SN1. SN2 का मतलब है कि वो nucleophilic substitution करेगा in one step and the rate will depend on both the halogenalkane and the nucleophile. But SN1 का मतलब है कि वो न्यूक्लियोफिलिक सब्स्टिट्यूशन करेगा इन 2 स्टेप्स. वो पहले कार्बोकैटायन बनाएगा और फिर उसको आने देगा. And the rate will just depend on concentration of that thing. So primary halogenalkanes prefer SN2. And अगर एग्जाम में लिखना हो तो हम क्यों लिखेंगे? हम दो बातें लिख सकते हैं. Number one, we'll say that the methyl groups or the alkyl groups around a tertiary carbon make it difficult for nucleophile to come in and attack. पहले तो ये बात होगी ना, वो उसको crowded कर दिया उन्होंने, वो आ ही नहीं पा रहा. And secondly, it is the carbocation on a tertiary carbon is more stable, and that's why it opts for SN1.
Sir, can you repeat these 2 points?
First point was that in the tertiary carbon, because of the other alkyl groups, it's very difficult for the nucleophile to access the central carbon. अगर इसका आपने Google करना है तो this is called steric effect of methyl groups. And the other option why this would occur, the other reason is that the carbocation on a tertiary carbon is much stable because of inductive effect of alkyl groups, and that's why it prefers SN1 mechanism. Again, SN1 mechanism क्या है? When it is a two-step process, पहले it leaves the halogenalkane that's already there, वो पहले चले जाता है, and then the new one comes in. And what's SN2? That it leaves at the same time as the new one coming in. अगर इनका मैं ग्राफ बनाऊं तो SN1 will happen in 2 steps. So S से जाएगा वो, obviously exothermic होएगा वन पे, और ये वाला S से जाएगा बस, the graph. And this point in there, this one, this is where the carbocation is made. तो ये जो थोड़ा सा उसको वक्त मिलता है ना, ये कार्बोकैटायन अपने आप को सस्टेन कर सकता है. SN2 में कार्बोकैटायन नहीं अपना बर्दाश्त
किस
करता.
चीज में ग्राफ है?
This is the graph of
Sir,
the
what-
energy profile diagram. Energy profile diagram. Remember who exothermic, endothermic wala? So this is the activation energy of the first step. This is the activation energy of second step. This is the activation energy here.
Where doesn't SN1 have one step?
No, it has 2 steps. The one in there is just to tell that rate depends on concentration of one substance, not 2. किसी एक रिएक्टेंट की कॉन्सेंट्रेशन पे रेट डिपेंड करता है. आपने रेट इंक्रीज करना है, आप जितना मर्जी न्यूक्लियोफाइल डालते रहो, अगर वो उस पर रेट डिपेंड ही नहीं करता तो वो तेज नहीं होगा रिएक्शन. SN2 मींस दोनों की कॉन्सेंट्रेशन तेज करने से रिएक्शन तेज हो जाएगा. इसे कंफ्यूज नहीं होना है. प्रॉपर्टीज ऑफ हैलोजन एल्केन्स, देयर इज ओनली वन प्रॉपर्टी लेफ्ट कि कौन सा ज्यादा रिएक्टिव होगा, बट आई थिंक वो हम कल करेंगे. डोंट वांट यू टू गेट कंफ्यूज्ड. So this mechanism, if you understand it, it will really help you out, not in just AS but in A2 as well. Again, जितना closely आप basic principles को follow करेंगे उतना ज़्यादा आपके लिए आसानी होगी. Always remember, negative is on a lookout for positive. The moment it finds it, it's going to attack. वो नेगेटिव एल्कीन में तो एल्कीन से अटैक करेगा. वो नेगेटिव बाहर कहीं पे है और आपके मॉलिक्यूल में पॉजिटिव चार्ज है, उधर अटैक कर देगा. एक ये डिफाइनिंग प्रिंसिपल है. दूसरा डिफाइनिंग प्रिंसिपल ये है कि जितना ज्यादा इंडक्टिव इफेक्ट होगा, जितना ज्यादा एक्टिवेटिंग ग्रुप्स होंगे, उतना ज्यादा वो चीज कार्बोकैटायन सस्टेन कर सकती है, उतना ज्यादा स्टेबल कार्बोकैटायन होगा. So tertiary will always have a more stable or higher chance of making carbocation, of adding more steps to the process, buying more time for the reaction compared to the primary one. तो प्राइमरी वाला ना थोड़ा सा स्लो रिएक्शंस भी होते हैं, सेकेंडरी वाले तेज रिएक्शन होते हैं. But of course we'll talk about which step is faster, which step is slower when we talk about that.